Okay, let's see here. All right. Okay, so let me continue. Okay, this is not what I want. Okay. So let me just briefly, since I forgot to turn on the live stream, I'm just going to put down the answer here that I had before. In fact, hold on. I don't think I have to rewrite anything. Let me see here. There should be a way of bringing, okay, I think this is it. I thought that was it. Okay. I'm just going to rewrite the answer here. For those of you who will be watching the video later on, this is the equation that was used, right? And we just put the numbers in, 0.500 m times e to the minus k, which is a rate constant, which is this right here, 6.32 times 10 to the minus 4 seconds to the minus 1, multiplied by 2 hours times 3,600 seconds over 1 hour. And the answer I got, as I said before, is 5.28 times 10 to the minus 3 m. All right? So that's basically how that is done. All right. Now let me clear this up and move on to the B part. So the B part says, how long will it take, in other words, the time required for 90% of N2O5 to decompose? All right? So basically, if 90% of the N2O5 decompose, that means that the concentration of N2O5 would be equal to 10% of the initial concentration of N2O5. So that would be 0.1 times the concentration of N2O5 initial, right? Which means that the ratio between the concentration of N2O5 and the concentration of N2O5 initial will be equal to 0.1, right? So as I said before, one form of the equation that can be used would be ln concentration of A over A0, or let me use the N2O5 instead of the A. So concentration of N2O5 over the initial concentration of N2O5 might equals to minus KT, right? So this implies that T will be equal to minus 1 over K times ln concentration of N2O5 over the initial concentration of N2O5. So that will be the equation you'd use because the question is asking for the time. So T will be equal to minus 1 over K, and K is equal to 6.32 times 10 to the minus 4 seconds to the minus 1 times ln, and this part here is equal to 0.1. And then we do the number crunching, and according to my calculation, this works out to be equal to 3.64 times 10 to the 3 seconds, or you can say 3,640 seconds. And that's how that is done. All right? Okay, any questions about this one? Any questions? Any questions? All right, so let me clear this and scroll down to C. Now C is asking, how long will it take for 90% of the, okay, I'm assuming they're talking about of the reactor to remain. Now in this case here, you're going to use the same equation as we did in B. So that equation would be T is equal to 1 over K, ln concentration of N2O5 over the initial concentration of N2O5. Now in this case, the K value would still be the same, which is 6.32 times 10 to the minus 4 seconds to the minus 1. But this time, the concentration of N2O5 to the initial concentration of N2O5 would be 90%. So here we're going to put 0.9, and then we do the calculation. And according to my calculation, this works out to be 167 seconds, and that's it. All right? Okay, so that's basically how C is done. And in the case of D, well, in the case of D, there are two ways you could do this. There's a long way and there's a short way. The long way would be using the same equation here, but this time, since the question says 50% here, we'll say T is equal to 1 over 6.32 times 10 to the minus 4, second to the minus 1, ln 0.5, right? Because that's 50%, that goes here. And then we work it out. And that would give the answer of 1.10 times 10 to the 3, right? Seconds. But there's another way of doing it, and that is using what is called the half-life equation, because the half-life, by definition, is the time taken for the concentration of the reactant to be reduced by half. And in the case of a first-order reaction, the half-life equation is this, ln2 over k, right? So basically, ln2 over the rate constant, which is 6.32 times 10 to the minus 4, seconds to the minus 1. And then we work that out, and you get the same answer, right? 1.10 times 10 to the 3. So both methods can be used, but this way is a shorter or simpler way, all right? Any questions about this? Any questions?
I have a question about.
Oh, wait a minute. I think I made a mistake here. Let me get my calculator. Let me see what I did wrong. I think I did something. Oh, my bad. Okay. There should be a minus sign here. And in fact, there should be a minus sign here. So please make that correction. For all the questions from, hold on 1 minute. For all the questions from B through D, there should be a negative sign in front of the minus 1 over k ln concentration of N2O5 divided by the initial concentration of N2O5. All right, so please make a note of that. I don't know if that's a question that somebody was about to ask.
Yeah, that was going to be my question.
Oh, okay, yeah. Right, so please make that correction, folks. I have it in front of me right here. I don't know how I missed it. All right, any other questions? Any other questions? All right, let me clear this. And scroll down. Okay, so the next question, it's talking about another reaction. This is the reaction right here. And the rate law is given right here. So basically, we can see that this is a second order reaction, all right? And the question is asking, firstly, what are the proper units for K, all right? So basically, to find the units for K, what we would have to do is rearrange this equation to get an expression for K, which is equal to the rate divided by the concentration of I squared. Now, the rate typically would be expressed in M over S, molarity over second, and the concentration would be expressed in units of M. So because the concentration of I squared, we're going to put M squared here. And therefore, when we simplify this, you're going to get M minus 1, S to the minus 1 as the units of K. All right? And of course, we're making the assumption that the units of time is seconds. All right? So that's basically the answer for A. All right? Now, in the case of B, the question is asking for the initial, well, it gives you the initial concentration of iodine, and you're to calculate the concentration of iodine when the time is 2.5 times 10 to the minus 7 seconds. Now, the equation that you're going to use for this is different from that for the first order, and it is this right here. 1 over the concentration of iodine at time t would be equal to 1 over the initial concentration, the initial concentration of iodine plus KT, all right? Now, the question is asking for T here, so that means that we have to rearrange this to get concentration of iodine. How am I going to do this? So what I'm going to do is, just put the numbers in actually. So 1 over the concentration of iodine would be equal to 1 over the initial concentration, which is 0.40 m, plus KT. Now, K is given as 7.0 times 10 to the 9, m to the minus 1, s to the minus 1, multiplied by T, which is 2.5 times 10 to the minus 7 seconds, all right? So what I would do is work out this part first. And when I did that, I got 1800 m to the minus 1, because this will cancel out with that, plus 1 over 0.40 m. And then when I work this out, this basically works out to be 1800 m to the minus 1. And the reason why is because 1 over 0.40, 1 divided by 0.40 gives you 2.5. So let me just show you how I got this here. So this part here works out to be 2.5 m to the minus 1 plus 1800 m to the minus 1. So this works out to be 1800 when rounded off appropriately, rounded off to the 100th place, like this. And then we're not finished yet, because remember, this is equal to 1 over the concentration of I, right? So what the question is asking for is the concentration of I. Let me do this up here. The concentration of I keep writing H instead of I. The concentration of I will be equal to 1 over 1800 m to the minus 1, which will be equal to 5.6 times 10 to the minus 4 m. And that's it. Okay, any questions about this? Any questions? Any questions? Okay, let me clear this and scroll down. Okay, so the next question is, if the initial concentration of iodine is 0.40 m, calculate the half-life. So basically, there's an equation that we can use to calculate the half-life for a second order reaction. And that equation is half-life, let me write it here. Half-life is equal to 1 over K times the initial concentration of A, right? So this is the equation that we can use to calculate the half-life of a second order reaction. So all we have to do is plug in 0.40 where this is and the K value, and we're going to get half-life is equal to 1 over the K value, which is 7.0 times 10 to the 9, m to the minus 1, s to the minus 1, times the concentration of A initial, which is 0.40 m. And according to my calculation, this works out to be equal to 3.6 times 10 to the minus 10. And the units here would be seconds, because this will cancel out with that. And this is what you're going to end up with. All right. Okay, any questions about this? Any questions? Any questions? Okay, continuing, let me clear this. And let me move on to question B, which says, if the initial concentration of 0.80 m, how much time will it take for 75% of the iodine atoms to react? Okay, so what that means is that the equation that I would use is 1 over the initial concentration of A. I'm sorry, 1 over the concentration of A is equal to 1 over the initial concentration of A. Or let me use iodine since that's what we're given here. So let me just change that to iodine plus KT, all right? So what the question is asking for is T. So we could rearrange this to get T is equal to 1 over K times 1 over the initial concentration of I minus, 1 over the concentration of I minus 1 over the initial concentration of I, all right? So the question now is, what is the concentration of I for the time that the question is asking for? And the key is right here. It says that it would take 75% of the iodine to react, right? So that means that the concentration of I would be equal to 25% of the initial concentration of iodine. So 0.25 times the initial concentration of iodine, all right? So basically, the way we're going to plug that into this equation is, well, we can calculate this first. The initial concentration of iodine is 0.80 m. So that's that works out to be equal to 0.20 m, all right? So now we can plug all the numbers in. 1 over K. K from earlier was, what was K again? K 7.0 times 10 to the 9. M to the minus 1, seconds to the minus 1, times 1 over the concentration of I, which is 0.20 m, minus 1 over the initial concentration of I, which is 0.80 m. And we need to do the number crunching. And according to my calculation, when I do this, I got 5.4 times 10 to the minus 10 seconds. And that's how that is done. All right? Okay, any questions about this one? Any questions? Any questions? Okay, let me clear this. Scroll down. Okay, so now we're going to move on to question number 7. And question number 7 deals with the concept of activation energy. And just to remind you, again, this was covered in the video lectures. The activation energy is basically the energy required by reacting molecules to basically be converted to products, right? So basically what we're saying here is that there's a certain amount of energy that the molecules that are colliding with each other must have in order for the reacting molecules to collide and perform bond breaking and bond making processes in order to get to the products, all right? So if the molecules do not have that minimum energy, then the reaction simply won't take place. Basically, the molecules will just hit each other and bounce off each other and therefore not react, all right? Now, there is an equation. In fact, there are a couple of relationships which are basically different ways of saying the same thing, actually. The main equation, I would say, which relates the activation energy to the rate constant is this equation right here. K is equal to A e to the minus EA over RT. So just to remind you of what these different terms mean. K is the rate constant, all right? A is the, if I remember correctly, it's called the collision factor. EA is the activation energy. R is the molar gas constant, which is 8.31 joules per mole Kelvin. And T is the temperature in Kelvin. All right? So those are the different terms in this equation right here, which relates the rate constant to the temperature. All right? And also to the activation energy. The A would be constant, if I'm not mistaken, at the same temperature, and R is always constant, all right? Now, basically, this value of K would be dependent, of course, on the particular value of temperature. So if you think of a situation such as in this question here, where you have two values of K and two values of temperature, we can actually have a relationship between those four terms, right? So let me just briefly describe that relationship. So let's say K1 would be the rate constant at T1. So K1 would be equal to A times e to the minus EA over R T1, and K2 will be equal to A times e to the minus EA over R T2, right? Now, if you divide one by the other, what's going to happen is that the A will cancel out, and you'll be left with K1 over K2 is equal to e to the minus EA over R times 1 over T1 minus 1 over T2. So this is a different way of expressing the first equation I showed here, right? This is useful because you can use it to solve problems like the ones that we have here, because you'll notice in this question here, we have a temperature here where the rate constant is this value, and then we have another temperature here where the rate constant is this value. So we can use this equation here to solve for, what's the question asking for? The activation energy, right? The question is asking for the activation energy, right? So basically what we have to do here is some more algebra where we find the natural log of both sides. You're going to end up with ln K1 over K2 is equal to minus EA over R times 1 over T1 minus 1 over T2, which means that EA, let me do it down here, EA will be equal to minus R times ln K1 over K2, all divided by 1 over T1 minus 1 over T2, right? So basically what I'm saying here is that this here would be T1, which is 300 degrees Celsius, which we have to convert to Kelvin. So we add 273 to this to give 573 Kelvin. This would be K1. This would be T2, which is 230 plus 273, which works out to 503 Kelvin. And this here would be K2, right? So we just put the numbers in, minus 8.31 joules per mole Kelvin, multiplied by ln K1, which is 5.70 times 10 to the, I lost it, 10 to the minus 1, or 5.7, not 5.70. 5.7 times 10 to the minus 1, m, s to the minus 1, m to the minus 1, divided by K2. What's K2? K2 is 2.7 times 10 to the minus 2, m to the minus 1, s to the minus 1, and then we divide all of that by 1 over T1, and T1 is 573 Kelvin, minus 1 over T2, which is 503 Kelvin. And that's basically the setup. And when I worked this out, I got 1.04 times 10 to the 5 joules per mole. And that's because these units cancel out. The Kelvin units cancel out here and here. So the final unit remaining would be joules per mole. And that's basically how that is done. Okay, any questions about this one? Any questions? Any questions? Okay, so let me clear this. And let me scroll down to the next question, number 8. Now, number 8, and I think number 9, let me just check something here. Number 8, number 9, and number 10. These questions deals with the whole concept of mechanisms of a reaction, right? And one of the things that kinetics is used for in chemistry is to determine the mechanism of reaction. So what do we mean by the mechanism? The mechanism is basically a description of the step-by-step process where you follow how the reactants are converted to products, all right? That's basically what the mechanism is. If you're given a balanced equation, it doesn't tell you straight off what the mechanism is, because the balanced equation only tells you what the reactants are and what the products are. It doesn't tell you anything about what happens in between as you go from reactants to products. So the mechanism of a reaction is basically a step-by-step description as you go from reactants to products. And this is very important in a lot of applied area of chemistry. For example, if you're talking about, let's say, for example, you plan to get into drug research, one of the things that scientists are always trying to understand is the mechanism of how the drug works. And a lot of kinetics, chemical kinetics is involved when it comes to understanding that, all right? And this is also true in certain industries where you're manufacturing certain products. Again, understanding the mechanism of the reaction is very important, because the mechanism can tell you, for example, which reactant is more important, what would happen if you, or it can predict to a high degree of accuracy, what would happen if you replace one reactant with something else? Would it be a more efficient reaction? And so on and so forth. So understanding what we'll be discussing here is important for your future careers if you plan to do medicine, pharmacy, if you plan to get into pharmaceutical research, etc. All right? All right, so let me see here. This question says, consider the following elementary reactions. So the elementary reactions in any mechanism is basically the fundamental steps, all right? And the question is asking, what is the molecularity of each reaction, and write the rate law expression. Now, the molecularity of the reaction is basically how many molecules are involved in as reactants in that elementary step, right? So for example, in the case of the first reaction here, you see that carbon monoxide is reacting with chlorine. So therefore, in the case of one, the molecularity is equal to 2, because you have one molecule here and one molecule here as reactants in that elementary step, all right? Now, the next question is asking for the rate law expression. It's very easy to write down the rate law expression for an elementary step. All you have to do is take into account the reactants in that step and write this down. Rate is equal to rate constant times the concentration of carbon monoxide times the concentration of chlorine. And that's it. That is the rate law for that particular elementary step, all right? Now, in the case of number 2, there's only one reactant here, so therefore the molecularity in this case is equal to 1. And the rate law in this case is equal to K times the only reactant, the concentration of the only reactant that is there, which is HCl. And that's it. All right. And that's basically how that is done. All right. Okay. So that's a relatively simple problem dealing with elementary steps. Any questions about this? Any questions? Any questions? All right. Let me clear this and move on to something a bit more complex. Now, in this case, they gave you this mechanism here, right? These are the individual elementary steps, all right? And you'll note that they say here that this step here is slow, and this step is fast, and this step is fast, right? So when it comes to several elementary steps, one after the other, right? What you'll find is that, very often there's one step that is slowest of all the steps that are present. And that step is known as the rate determining step. All right, the rate determining step. And the reason why it's called the rate determining step is because that step determines the overall rate of the reaction, right? So the overall reaction rate cannot be faster than the rate of the slowest step, the rate determining step, all right? Now, here they're asking in question A, identify the intermediate and the catalyst. So here's a difference that you need to understand between the intermediate and the catalyst. The intermediate is something that is produced in one step and then used up in a subsequent step. All right? So the intermediate is produced in one step and then used up in an subsequent step. The catalyst is a substance which is used up in a previous step and then produced in a latter step. All right? So that's the difference between the intermediate and a catalyst. Maybe I should write this down. So the intermediate is used in an earlier step and I'm sorry, I'm having the terms confused. Is produced in an earlier step, and used up in a subsequent step. All right? So that's the intermediate. Now the catalyst is used in an earlier step and produced in a later step. All right, so that's the difference between an intermediate and a catalyst. So based on what I just described here, right, let me hear what you think would be the intermediate and the catalyst in this reaction. And please note, you can have more than one intermediate, all right? Just to let you know, all right? Okay, so let's deal with the intermediate first. What do you think would be the intermediate or intermediates in this reaction?
The 2Cl.
The 2Cl, so you can't just put Cl, you don't have to put 2Cl. That's one. And what's the other? Is there any more? Any other intermediate? Remember, the intermediate is produced in an earlier step and used in a second step. Okay, I see two responses in the chat. Let me see here. CLO is correct. So that was stated by Brianna. So CLO would be an intermediate, right? As well. So these are your intermediates, all right? Okay, what about catalyst? Now remember, catalyst is used in an earlier step and then produced in a subsequent step.
Cl2.
Cl2 is correct. So this would be your catalyst. All right? Very good. All right. So that's the A part. B is asking, what is the I keep messing up this word. What is the molecularity of step 3? So this is step 3 right here. Remember what we said the molecularity is. It's the number of molecules in that step of the reactant.
One.
Mm-hmm.
What?
You sure about that? Hint, hint, hint.
2.
Exactly. There are two molecules of that. It's the same molecule, but it's two of them. So therefore the molecularity is 2. Okay, let me clear this. Okay, so the next question is, which step determines the reaction rate? And write the rate law for that step. So if you remember what I said earlier, what step determines the reaction rate in this case?
Is it
Step
step
one.
one?
Step 1, exactly. Step 1, because it's the slowest step, right? Now, the next question is write the rate law for that step. So what would be the rate law for that step?
K times the concentration of Cl2.
Rate is equal to K times the concentration of Cl2. And somebody's saying something in the chat. I don't know if they're saying the same thing. Yes, okay, so that is correct. Okay. Let me see here. Okay, let me clear this first. And okay, now for this question here, I want us to ignore, I should have taken this out, this part here. Ignore this part right here. All right, so the only thing I want you to write down is the overall reaction equation. Now, something I should have mentioned earlier, and that is that if the mechanism is to be seen as legitimate, then basically when you add up all the steps in that mechanism, you should get the overall reaction, right? Or the overall equation. So basically we're going to do that in this case here. Now I'm just going to rewrite the mechanism here. That's the first step, and then the second step is 2NO plus 2Cl to give N2 plus 2ClO, and then here I'm going to write down 2ClO plus, I'm sorry, not plus, then the arrow, and then Cl2 plus O2. All right, so whenever you're adding equations together, of course, and this is something that you should have learned from your Chem 1, when you're adding equations, then basically you cancel out those items that are common to both sides. In this case, that would mean that these two chlorine atoms will cancel out here and here. These two ClOs will cancel out here and here. And these chlorines will cancel out here and here with 2NO to give N2 plus O2, and this would be the overall equation for the reaction. All right? So that's basically how the D part is answered. All right. Any questions about number 9? Any questions? Or number 9D? Any questions? Okay, so let's move on to the next question, which is number 10, after I clear this. So in the case of number 10, you're given a proposed mechanism for this reaction right here. And there's another correction I need to make here, another typo. Let me just include that. There should be a K here, so please include that in your assignment, right? There should be a K there, right? Okay. Now, this question, they gave you the equation, they gave you the overall equation, and they gave you a proposed mechanism, right? So this is the mechanism right here. Take this out. So this is the mechanism right here. They gave you the first step, which is a reversible reaction, and then the second step, which goes in one direction, and then the last step, which is a reversible reaction, all right? Now, in order for you to see whether or not this mechanism is in alignment with the rate law here, what you'd have to do first is focus on the rate determining step, right? Which of course is this step, the second step right here. And you're going to write down a rate law based on that step. Okay, so let me just scroll down here. If you were to write down the rate law based on that step, you're going to end up with rate is equal to K2, right, times the concentration of N2O2 times the concentration of H2. All right, so this here, let me scroll back up here so you see what I'm talking about. This here is a rate law for this step right here. The concentration of N2O2 times the concentration of H2, and the rate constant would be K2, all right? Okay, now the problem with this, as it is so far, is that the N2O2 is an intermediate. And in practice, it would be very difficult for you to determine the concentration of N2O2 experimentally. And the reason why is because it's an intermediate, as soon as it is produced, it's used up. So therefore, it's very difficult to determine, and I would say probably impossible to determine experimentally the concentration of N2O2. So what we have to do is find the concentration of N2O2 in terms of actual things that we can measure, right? So that leads us now to the first equation of the first step of the mechanism, which is this one right here, right? According to this, this goes in both directions. In other words, NO2 will react to form N2O2, and N2O2 will react itself to get back to NO2, right? So what we'll be doing is assuming that this is an equilibrium situation, right? So basically, if it's an equilibrium situation, that means that the rate of the forward reaction, right, would be equal to the rate of the reverse reaction, right? So the rate at which NO2 reacts to form N2O2 will be the same as the rate at which N2O2 will react to form NO, all right? So we can, let me scroll back down, so I can write down what I just said. So therefore, we can say that the rate of the forward reaction for the first equation would be K1 times the concentration of NO squared, and that would be equal to K minus 1 times the concentration of N2O2, all right? Now, in this case here, we have NO, which we can measure directly because it's a reactant, and we have N2O2, which is an intermediate, as I said before, very difficult to measure, if not impossible, right? So what we can do is express this in terms of NO, and therefore all we have to do to get that is to write down that the concentration of N2O2 would be equal to K1 times the concentration of NO squared over K minus 1, right? And then what I would do is, because we have the concentration of N2O2 expressed in terms of this, I can basically plug this here where the concentration of N2O2 is, and the result of that I'm going to put right here. Rate of the reaction will be equal to K2 times K1 times the concentration of NO squared times the concentration of H2 over K minus 1, all right? And if you look at this equation here, you'll see that that equation is pretty much the same as, let me scroll back up here. It's pretty much the same as this equation here. Now remember I said that you should have a K right here, right? So basically this equation and this equation is the same thing, where K is equal to K2, K1 over K minus 1, all right? So therefore the answer is that, well, we have just shown that the proposed rate law, which is what we have here, basically is what is predicted by the mechanism, because we basically use the mechanism to derive this equation right here. All right. And that's basically how that is done. All right. Okay. Any questions about this one? Any questions? Any questions? All right. So let me
I have a question.
yes, ma'am.
So we don't do with anything with the third equation? So it's
No,
just the first
no.
and second?
Exactly.
Okay.
Exactly.
you.
And the main reason why that is the case is because the rate determining step comes before the last equation. So it doesn't matter what, the speeds of the reaction in the case of the last equation, because that reaction is faster compared to the rate determining step. All right. Okay. So the final answer to this question is that the mechanism is consistent with the rate law. And that's it. All right. Okay, let me clear this and scroll down. Okay, so the questions being asked here, would have been covered in the videos. Let me just check something here. Okay, so let's go through each of these here. The question is asking for you to describe the differences between the following. And the first one is a catalyst and an intermediate. And we just looked at that earlier. So what's the answer? What's the difference between a catalyst and an intermediate?
A catalyst is used in an earlier step and then produced in a later step,
Right?
as an intermediate is produced in that earlier step and then used in a later step.
Okay, very good. So that's basically it for the A part. All right, what about B? Absorption and adsorption. Now, this particular topic, well, the adsorption part of it deals with catalysis and more specifically, heterogeneous catalysis. Basically, a catalyst is a substance which, as I don't remember who said that, but the young lady just said the catalyst is basically used up earlier and then produced later, right? And in doing so, it speeds up the reaction rate, right? So the actual definition of a catalyst is it's a substance which, when added to a reaction, speeds up the reaction rate but remains unchanged at the end of the reaction. Now, there are two types of catalysts. You have heterogeneous catalysts and homogeneous catalysts. In the case of heterogeneous catalysts, and I think the example I used in the videos is the reaction between nitrogen and hydrogen in the presence of, if I remember correctly, palladium. And basically, that's where the term adsorption comes in, right? So maybe I should just explain what adsorption is. Adsorption is where you have molecules sticking to the surface of another substance. And usually the other substance is a solid, all right? So that's adsorption. And then absorption is where we have usually a liquid that is soaked up into a porous substance. And that porous substance could be something like paper or, you know, anything that's porous, that has very tiny pores. All right. So that's basically the difference between adsorption and absorption. All right. Okay. Okay, so that's B. In the case of C, what's the difference between homogeneous and heterogeneous catalysts? Can anybody tell me? What's the difference between a homogeneous and heterogeneous catalyst? Okay, write this down. A homogeneous catalyst is one that is in the same phase as the reactants, right? A homogeneous catalyst is a catalyst that's in the same phase as the reactants. A heterogeneous catalyst is one that is in a different phase as the reactants, all right? So that's the difference between a homogeneous and a heterogeneous catalyst. All right, okay, D, first and second order reaction. Can anybody tell, you should be able to tell me what's the difference between a first and a second order reaction? Well, we just discussed it earlier. What's the difference between a first order reaction and a second order reaction? Okay, so in the case of a first order reaction, the rate of the reaction, this is for first order. The rate of the reaction is directly proportional to the concentration of the reactant. All right? While in a second order reaction, the rate of the reaction is directly proportional to the concentration of the reactant squared. All right? So that's the essential difference between the first order reaction and the second order reaction. All right? The first order reaction, the rate is proportional to the concentration of the reactant. Second order reaction, the rate is proportional to the concentration of the reactant squared. Okay, what's the difference between average rate and instantaneous rate?
Average rate is the average of the rate over time, and instantaneous rate is the rate at a certain point in time.
Okay, so repeat what you just said for the average rate.
So average rate is it's the average of the rate over a period of time.
Well, actually, it's the change in the concentration of reactant. In fact, let me make it simpler here. The average rate is the change in the concentration of either the reactant or product, it depends, divided by the change in time. Sorry about that. And the instantaneous rate is the rate of change of the reactant or product concentration at a particular instant. All right, so that's the difference between the average rate and the instantaneous rate. All right, continuing. Okay, so number 12 deals with determining the rate law of a reaction based on data that's collected. In some textbooks, they call this the initial rate method. And what I'm going to do is, in the interest of time, is do the first one. Let me just check something here. Okay, if I'm not mistaken, give me 1 minute here because I think oh, I remember now. Hold on. Okay, I should have published this. Let me do this. Oh, I thought, hold on. Yes, I think this is the one right here. Let me see here. Okay, so I should have published this folder here. This has some more questions of the same type. So let me go back here. Let me publish this here. So you need to do this question. This handout here. You need to work on this one as well. So let me remove this one to avoid confusion. Okay, so let me go back to this here. So the method I'm going to use here is very similar to the method that you're going to use to solve the rest of this this assignment, including the one that I just published, all right? So in this particular case, we have a reaction where there's only one reactant, right? And the question says that you have to use the data, which is provided here. Now, the data that is given is the concentration of the reactant and then the initial rate for each of the concentrations, all right? So they do different runs, experiment 1, 2, and 3, and get the data values, right? And the question is asking for you to find a rate law, right? So basically, this is what you're going to do. You're going to compare these two first, and I'm going to write down a general rate law first. So the general rate law would be rate is equal to K times the concentration of ArSO2H raised to the M, right? So M would be the order, K would be the rate constant, right? The idea is to find M, right? So for experiment 1, what I'm going to do is plug these numbers into this equation. I'm going to end up with 4.75 times 10 to the minus 5. M over S is equal to K times 0.25 raised to the M. And then for experiment 2, 6.84 times 10 to the minus 5. M over S is equal to K times 0.30 raised to the M. And by the way, these should be molarities here and here. And then what I'm going to do is divide the top by the bottom, and the K's will cancel out. The 10 to the minus 5 and these units will cancel out. These units will cancel out. So this will simplify to give you 4.75 divided by 6.84, and that will be equal to 0.25 over 0.30, all raised to the M. And then when I work out this part, I got 0.694. And this part works out to be 0.833 raised to the M. So how do we get M? Well, if you remember from your algebra courses, if you want to solve for this right here, you'd have to find the log of both sides. So I'm going to do that up here. Log of 0.694 will be equal to log of 0.833 raised to the M. And then I would bring this M down here. So that would be equal to M log of 0.833. And then I would solve for m, which would be log of 0.694 divided by log of 0.833. And according to my calculation, this works out to be 2, all right? So therefore, the rate law, where am I going to fit this? The rate law for this reaction is going to be equal to K times the concentration of AR SO2H squared. And that's basically the final answer, all right? Okay, any questions about this one? Any questions? Any questions? Let me do a quick check of something here.
Could you have done the same thing with 2 and 3?
Yes, yes, exactly. Give me 1 minute here. Let me okay, yeah. Yeah, you could do the same thing with 2 and 3. Okay, any other questions? Any other questions about this one? Okay, I think I'm going to stop here for today. I'm going to leave the rest of the problems for you to do. Now, because of what happened last week, Monday, remember I told you guys that I would have put off your first test until next week. Now, we're still not finished with this assignment yet. In fact, you have to complete it on your own. So I'm thinking of putting off the test for yet another week because of what happened on Monday. So that test won't be given until the week of the 23rd to the 27th. All right. So what I'm going to do is right now, I am going to, well, let me clear this first. And let me, okay, let me get out of this here. And let me go to assignments. And I'm going to open up the Dropbox for assignment number 2. So today is the 9th. Okay, so I am going to let it be due on the 11th. And the reason why is because I want to grade it and get it back to you as soon as possible. So that you can have it to review for your test. Let me go here, and let me go here. Whoops. And let me go here. Okay, so it's going to be due on the 11th. All right. And also, I'm in the middle of grading your assignment number 1, so I'm hoping to get that to you as soon as possible, hopefully by tomorrow. All right. So let me save this now. And that's pretty much it, right? Remember, when you're submitting your assignment, make sure that you submit it as a PDF document, right? And make sure that you write your name on each page. And some other things I need to remind you of. So I'm going to post those reminders in Canvas in the announcement section, all right? Okay, so in the 5 minutes that we have left, are there any questions? Any questions? Any questions?
Next week,
Huh?
I got a for next week. I got a notification. For next week, I got a notification that school was going to be canceled on Monday. So are we still going to have virtual class? Or?
Oh, shoot. Seriously? All right. I just saw the email this morning. That's supposed to be like George Washington's birthday or something like that. Oh,
Yes.
that's really messing up my, my schedule because that, oh gosh. Okay. Yeah, I guess we won't have class on Monday of next week. The because I was hoping to start the next chapter next Monday. And that's really pushing us. Okay, yeah, so there will be no class next week. All right, so yeah, that's it as far as that is concerned. Okay, any other questions? Any other questions?
So, to understand this, since we're not having class next week, are we still having the test on the 23rd?
Yes, because that test will cover everything up to this chapter here, 1 and 2. I mean, assignments 1 and 2.
And my other question, so in other words, the study guides are the assignments.
Exactly, the assignments and the answer keys to the assignments, which I will publish also. I would also recommend that you try to do as many questions from the textbook, from the relevant chapters in the textbook. All right?
Will the test be online since
No,
we're
it's
not
going to
in the
be
room?
it's going to be in a testing center. So you would have
Okay.
to sign up for the appointments for the test. And I don't know if I told you guys this, but I got an email from the testing center saying that in the past there have been issues with students not turning up for their scheduled tests, right? And that kind of creates a situation for them where the amount of space is limited, you know, in the testing center. And in some cases they had to turn back some students because of the already occupied times, even though the students didn't show up. So please, if you made an appointment for a particular date for a test, make sure you meet that appointment. If you can't meet that appointment, let the testing center know ahead of time so that they can, you know, make other arrangements. All right. I'm going to say all of that in the announcement that I'm going to post later on. All right. Okay. Any other questions?
Or when we turn in the assignments, does it have to be on the, do we have to print out the document that you give us and put all our answers on there? Or can we
Yeah,
just
you
have
have
it
to
on?
do it. You have to
Okay.
do it. You have to do the assignments on the original document.
Okay, thank you.
All right. Yes. Any other questions in the remaining 3 minutes? I'm sorry, 2 minutes.
Are we submitting the additional kinetics questions with
Yes.
assignment two?
Exactly. Along with the
Okay.
initial one. Yeah.
Okay, thank you.
Mm-hmm. Any more questions? Going once, going twice. Okay, so that's it, folks. So I won't see you next week. I'll see you the week after. All right. Okay, take care. Oh, somebody was asking a question. Will you give us the old test key for test number 1? Let me see if I can publish that right now. Okay, pass test key. Let me see what this has here. Okay, let's see. Let me open this up. Okay, that's not a key. Okay, hold on 1 minute. Let me try this one here. Okay, so this here. Okay, so I'm going to publish this one here. This is a pass test key. I think this is a good one to look at to prepare for your Okay, so let me go here. Let me publish this right here. And let me also publish the past test key folder. I think that's already published. Hold on. Okay, yeah, it's already published. All right. So you can use that to help you to prepare for your test as well. All right, so got to go. I'll see you guys week after next.